Strong solutions, which yeah, and then we also talk about results in critical spaces, and this is what I finished the other day in special spaces that were global in time for large data in 2D. In 3D, we needed a smallness condition or local in time. So today, I want to talk about inhomogeneous Navier-Stokes, which is the same fluid equations, but now we allow the density to vary in time and space. So we have raw the density multiplied by the acceleration. Here now the viscosity, in principle, can depend on the density. The density satisfies the transport equation, so this is conservation of mass. Again, we have incompressible fluids, and for the viscosity, I just state that is a smooth function of the density. And okay, so for this. Well, this equation, we can also write them because of the incompressibility condition. Mu is the viscosity. So this case is as if here you put mu divided by rho, both of them constants. This equation, if we want to talk about weak solutions, I will not really talk about them, just to state the result. It's better to write them in the so-called conservative form. Same for the density. So from here, the definition of weak solution is just the integral parts and with the test function, so that everything is well defined. So the question for this problem is, okay, all these theorems that we had for homogeneous hold for inhomogeneous. And some of them, yes. We have the similar result for Lereyhoff, so-called Lereyhoff solution. So we have that if now we have to talk, we cannot just say the initial velocity, but the initial momentum, because here we always have rho times u. So if the initial momentum belongs to L2 with incompressible condition on u, the initial density is in L infinity and non-negative, then exists a global in time weak solution that satisfies the energy inequality, which in this case, just taking inner product with u and integrating by parts, one obtain this. I haven't defined. Yes. And here I haven't defined. This is the symmetric gradient. And the only difference with the homogeneous case is that in the homogeneous case, we had that this solution in 2D were unique. the Lereikhoff weak solution. And in 3D, that was a big open problem. So here, even in 2D, uniqueness is not known. In the homogeneous case, the uniqueness was basically a consequence of the energy inequality. Plus, when we took the energy estimate, at some point we used the Lisenskaya inequality, and all the powers match. And in 3D, that was not right, and we had a bigger power, and to control it, we needed the initial data in H1/2. But that was out of the weak solutions case. And we mentioned that part of the reason of that was, in some sense, a consequence that the 2D Navier-Stokes was critical with respect to the scaling and 3D supercritical. Here, why uniqueness is not known? Well, the main reason is this equation, the transfer equation for the density. If one just tries to do the standard argument for uniqueness, let's U1, U2, rho1, rho2, two equations. In the second one, U1, rho1, U2, rho2, two solutions. Let's say then that, yeah, right now I don't grab the viscosity. And use the second equation, one obtains just the time derivative of the difference. Maybe I'm not sure if the index are correct, but basically that. So I guess it depends on which difference I'm doing. It doesn't really matter, okay? So I check rho1 or rho2, and here the same, it doesn't really matter. The important thing is that we have a transfer equation and a force which loses one derivative, and rho for the weak solution is only in infinity. So we cannot lose any derivatives here. And we cannot expect any gain of regularity because this is a transfer equation. So then that is not going to work. And later in the theorem I will talk today, this will be again a problem. Like this method will not work, and then one has to find a different way to prove uniqueness in homogeneous Navier-Stokes. So some other results. But if the initial data, well, let's say U0, rho0. If this is a smooth and rho0 not zero, so it's strictly positive, and this is smooth, then everything is basically as the typical Navier-Stokes. You have a strong solutions which are local in 3D, global in 2D, and all this kind of thing. And the proof for this is not very different to the proof we did in the very first lecture, like energy estimates and compactness. So the main difference apart from this is if we get in between, if we try to get results in critical spaces, I first need to define the scaling for inhomogeneous. If rho u are solution, then rho lambda given by this scaling and u the same as for. Then this is another solution, and from this one can check that critical spaces are for rho, for example, h d halves in RD. For U0, like in Navier-Stokes, h d halves minus 1. In homogeneous, so for classical Navier-Stokes, one had Fujita, Kato, theorem that gave the closeness or existence and uniqueness in H in this physical space. For inhomogeneous Navier-Stokes, this is again not known in the scale of solid space. And also, if one replaces this is at the same level as L infinity, this is also not known. If one takes rho 0 L infinity U0 here, this is not known. So the only results that are known for critical are some of them, well, or the ones I know, in best of spaces. And just to give one example of them, which is from last year. There are more, okay, and this is like maybe the sharper one in 2D, but there are another one in 3D. So in this one, they have U0, and this is for R2. Not in L2, but a bit more than L2. And the important part, or the part that everyone would like to remove, is that rho 0 has to have some regularity. So for these spaces, they have a global existence without a smallness, but for uniqueness, at least one needs rho 0 with one derivative. So more than H1. I don't know exactly the proof of this, but yes, I mean, I can see it. Basically, if you don't have this, if you have less regularity, you are not going to be able to control this. I don't know if it appears somewhere else, but yeah, I can see that you need one derivative. Okay, so this is all I want to talk about previous results. Just to mention again this part, that for uniqueness, rho 0 is more than in H1 to obtain some. So, related to all this, the problem I want to mention, the one I've worked on, and that was also active in the last year, very active, was the so-called density patch problem, or Leon's problem. This is just because it appears in his book of 1996. And basically, the problem was this: if we have now initial density, which is given by two constant values, and this is some domain d0 and some initial velocity, okay, to be specified, then at another time we want to know if the regularity of the initial interface is propagated in time or not. That the structure is propagated, it's more or less straightforward because we have the transfer equation. So this was already known from the weak solutions by Leon. The other part is not that clear, to check that the propagation is that holds. And the first thing mentioned, this result doesn't belong to the previous one. So the density, yeah, rho, if we think of it as the global, as a function in the whole space, is only in L infinity. So. Yeah, I will explain the theorem. So basically, the question is if the initial interface is, let's say, C1 gamma, is it true that this is also C1 gamma for all time? And the same question for different levels of the regularity. And okay, so here I'm assuming, so well, I haven't mentioned, I'm assuming here mu constant. Okay. One can also pose the question with the variable mu. And my intention today is prove this result for C1 gamma. It will be, I think, a short proof. So I think I can do it. And then I will try to mention the additional difficulties when one has variable viscosity. And I will do this one because these two ones turn out to be slightly harder. Okay, so let gamma be between 0 and 1, S, which will be just some number very close to 0 for our purposes. Go 1 and go 2 is strictly positive. Then I will mention about this restriction. U0 in H gamma plus S. Divergence free. And the initial data is such. Then we have, I haven't said that. Well, this is not good. This is not really bounded similarity domain. Then, for any positive t, here the notation ddt is the transport through the particle trajectory. So ddt, and it's just the flow. And all the regularity we have for U is U continues in the lower norm, L1 in time, C1 gamma plus S tilde with S tilde less than S. So these are just, as I said, very small numbers. Okay, this we will see where all these quantities appear. So this is just information about the regularity in space and time for you. For what? And dt, yeah, I should say here where dt. So this is the regularity. I mean, this is the main part of the theorem. This is just the information one needs to prove this. No, it never touches. And this is like both the propagation of regularity and the fact that it doesn't touch, it will be a consequence that one has enough regularity for. So in fact, this particular case with only C1 gamma regularity, we will see that you don't really need the structure of a patch. You can, if you have the initial density in L infinity, we will obtain enough regularity for you that it propagates all these kind of structure. But if you want to go higher, then it's not. Then you really need a patch. Okay, so for the proof, the scheme of the proof would be first estimates for you, global in time estimates for you, then estimates for UT, transfer the regularity from UT to you. All this is just to prove enough regularity for you, and then the system proof, I mean the proof of existence, is modifiers and compactness. I will not mention anything about this part. And the last part is uniqueness. I will also not do this part. I will mention it because in fact this is maybe well, I mean this is not trivial because of what I said before, but I will just mention why it follows. Okay, so let's start with this part here. So the point one is just energy inequality. Take inner product with U. So here, mu is a constant, and in particular, 1. So from here, I said before, one obtains the energy inequality, and then okay, we need more regularity for you. The natural thing in the second step would be if we want to obtain U in some solid space like H gamma plus S, take fractional derivatives here and take inner product. We cannot do that because we have rho, which is only in infinity. So instead of that, we are going to study regularity for UT. So take inner product of this equation with UT. And this is a trick also used in compressible Navier-Stokes. The last term disappears because of the incompressible condition. And this is nice, and it will not happen when we have viscosity jump. Okay? So we don't have to think about the pressure. And now I'm going to use this condition, which will make everything easier. we have row 1 and row 2 bounded from below, and I should have said these are constant, so this is also in an infinity. So now I remove row. I'm going to put row max or the L infinity norm of row. And I have u grad u, ut. Yeah, so I'm going to put ut in L2, u in L4, gradient u in L4. Now you can see that this one here, we want to absorb it with this one here. In general, I cannot do that because I have this square root of rho. But because I am assuming that they are positive, this is bounded from below. So I will do that later. Let me finish this part. L4 and L4, we use the Liechtenstein inequality because we are in R2. And this I will just some constant C. Okay. And right now we have two derivatives of u, and here we only have one, so we need to do something to absorb this term. And more or less, I mean, one should expect that two derivatives of u, population of u, is at the level of ut. So somehow we want to bound this term by ut so that we can absorb it. And for the constant viscosity case, like we are here, this is we can say easy because we have divergence and gradient. So we have Laplacian of u. Yeah, Laplacian of u equal to this one. So because this is a divergence and this is a Laplacian, if we take the L2 norm, we obtain this I again bounded. Let me just see. And again, I do the same as I did before. So L4, interpolation of the L4 by L2, square. Yeah. Here, Helder, so a square is one of them. This one I don't care because this is controlled by the energy inequality uniformly in time. So this is just a constant. And now the second one, C, now appears to the power 4 and the Laplacian. I can put, for example, 1/2. Sorry, the second derivative of u squared. And now I can absorb this term by this other one. It doesn't matter that we have here like any combination of two derivatives and here the Laplacian because this is in L2, so we have like raised transforms. So in the end, what I'm saying is that two derivatives of u in L2 are controlled by the L2 norm of ut plus u L2 divided u L2 squared. This is in principle okay. We control, at least we have some information about this from the energy inequality, and this is what we want to obtain so that now we can absorb it. So let's finish this. We obtain I can remove the row. I bound it by the minimum. This is less or equal than, I put this square and this square. So and again here, I plug this in. Here I did tender, so a square and a square. This absorb it. I have a square of this one. And now here, use this bound. Repeat the same, absorb it. We only have this. And now this, if you want, we can write it a square and a square. So ground one. And this constant depends on the L2 norm of UC. Here, in all the bounds, I was removing, for example, the bound for the L2 norm. And when I use ground wall, I'm using here that the L1 norm in time of, sorry, the L2 norm in time of the gradient of U is controlled through the energy inequality by the L2 norm of the initial data. So we conclude this. But okay, this is okay, but so far this is useless because I'm assuming the initial data is 1. And we only had H gamma classes. And in particular, for example, I want to do it with gamma very small and check it. Okay, so now to obtain this for gamma plus S, we have to do some interpolation. And the idea, like all the problem as at the beginning, is that we cannot take derivatives in space. No, we have to use always time, like multiplying by ut or so. So now, if we want to integrate in space, what we do is we multiply by a time weight. So we multiply by a power of t, and we will redo this balance and check that we can close it just with u0 in L2. Basically, the idea comes from this fact that one can characterize Sobolev norm. So this is something more or less standard. Basically, what I'm saying is that if I have the heat equation, so this is the solution of the heat equation with using initial data. If I multiply by t, I'm integrating twice in space. Right? So I'm just mentioning this so that the power of time that we need, if I put s equal to 1/2, here I obtain u0 in it. Supremum for Okay, and probably it's 40 near 0. Yes, yes. Everything here, it's, in fact, it's near 0 because now the weight I have to put, I won't going to write, so I will say repeat everything with time weight T, but I should be saying better sigma T, the minimum of T and 1. I only want the time weight for a small time. And okay, I skip the steps, but what one obtains is well, I should say something more. Because I want to do interpolation, I'm going to use linear operators. So I will think of my equation. I will, let's say, linearize the equation. So now let's talk about B with the velocity given by U. So this is my actual velocity. So now, if we want to repeat all the estimates that I did, being careful by splitting B and U, like they are different things, then one obtains E and also the one before. Okay. And now I will just state the interpolation theorems that I will apply. One is raised to n, and the other one is Stein. So basically, the linear operator that I consider is V0 equal to gradient of P. And then what we have here is EV0 in L2 less or equal to time constant V0 H1 minus 1/2 and okay, so interpolate, and basically you obtain the constants to the powers corresponding to the interpolation of the solved left node. So CT minus 1 plus 1 plus S half V0 in H1 plus S. And this is how this, in the statement of the theorem, we have this kind of powers. If you want to check the power, this comes from well. And then the other interpolation that I need, this is giving me the regularity for V, the gradient of V. So I can do the same, like not the same, but another interpolation to obtain information about VT. Okay, so this is define the operator TC V0 with C a complex number such that the real part is 0, 1. This is, for example, in Grafacco's book, Stein's interpolation theorem. So here the y will disappear when we take the norm, and this is from the time weight that we included. Okay, so where are we? So far, we only had let me state what is the regularity that we have obtained so far to check how far we are from our goal. And so this is what we have obtained. We want to propagate regularity for the interface, or in particular, we want to prove uniqueness of solution. So the crucial quantity in all this result is to obtain that the gradient of U is in L1 time L infinity, so that we have X, the flow, well defined. So we have particle trajectory, and then with this, in principle, all the structures are propagated correctly. If we wanted to propagate C gamma interfaces, so let's call C the interface, the parameterization of the interface. This is just the transport of the initial interface. So to study C1 gamma regularity of this, basically taking derivatives and using the definition of the equation for the flow. What one needs is gradient of U in L1 time. Okay, so this is just a comment about the level of regularity that we need for the velocity. Just looking at each trajectory. Okay, so right now we are very far because we only have U in H1, and here we can think of this from the previous estimate as two derivatives of U, but still in L2. Okay, so we don't reach, for example, infinity. So here I will skip many details, but I will mention what's the idea. Not many details, just some computation. How do we obtain high regularity? Well, again, we have to use time. So before we did the equation times u, the equation times ut. So now derivative of the equation in time times ut. And in fact, one can continue this even slightly more, taking twice time derivative and multiplying by u. But so far, this is the only one that we need now. And okay. Yeah, I'm not going to do this. I just mentioned. So if one starts doing this, taking the derivative of the equation, you can see that we will obtain terms, for example, like these ones. Some others. Taking a product with ut, the pressure will disappear. So this is okay. And in all these terms, we have to use that rho t is minus u derivative of rho. And then integrate by parts. So there are no partial derivatives of rho. And all the terms after that, all the terms can be placed in the adequate space with time weight. Inner product with ut and I think it's 2 minus 2s. Introduce the time weight so that everything matches. And now we don't need to do interpolation. If we put this time weight using the previous balance, everything will close and we will obtain okay, so here, what is this saying us? Notice that this balance, it's only for ut. We need the regularity for u. But here we are saying that u is in all spaces between L2 and H1. So, sorry, ut. So ut is interpolating these estimates. I have it somewhere here. So ut is in some LQ time H gamma plus S tilde with Q, well, some number. The only important quantity, the only important fact here is that Q can be taken including 1. Okay, so we have this in L1 time H gamma plus S tilde. And now, let's use Stokes again. We have that gradient of u. And this is our equation. Let's take the ray projector. The pressure disappears. Now, this is an H gamma plus S. So in particular, we can use an embedding. This is in L1 times LP for P, so P is minus 2P equal gamma plus S minus 1, no? So 2, in particular, bigger than 2. And this is the important thing. P here can be taken bigger than 2. But of course, we want the exact relationship with gamma. But the thing is that because this is bigger than 2, this is a ray projector. This is incompressible, so we can just remove this. And then U is in L1 time W 2P. Okay, because rho is just in L infinity, so all this thing is again in L1 LP. And this, by embedding, is in L1 time C1. If you do the numbers, it's here. In particular, P is bigger than 2, so U is more than H2. So gradient of U, we see, of course, it's in L infinity with some more. And basically, this concludes the propagation of regularity. And now, if one wants to do uniqueness, the proof is different to this. The difficulty is what I mentioned before, the equation for the rho. But if one works in Lagrangian variables, then rho is just it's constant in time, so that equation disappears. And because we have a gradient of U in L1 time L infinity, then gradient of X of the particle trajectories are, I think, also here. Yeah. And therefore, one can write all the equations making a transformation with the particle trajectory. So write the equations in Lagrangian variables. And there one can do uniqueness. Okay, so some comments I will mention and I finish. So two assumptions that were crucial in all these results. These are open questions right now. What happens if one of the densities is 0? So this is not known in R2. It's known, so the result holds almost not the same, like the proof changes quite a bit, but okay in the torus or in a bounded domain with enough regularity. And the main reason is that here one can use some version of comparison inequalities. So all the problem with rho is 0 is that in the energy inequality you have this quantity, and on the other side you have quantity that only has U. So you cannot control with this one. But if you can have some kind of comparison inequality, then you can control U by gradient of U, and in the energy inequality you also have this quantity here.
Physically, it was the point.
It was too, well, yeah, physically this would correspond. For example, here fluid and here value, or the other way around. This is not true. Like physically, this is I'm cheating here because the viscosity was assumed constant in all the space. So you have incompressibility both here and here. So for vacuum, you need both rho 0 here and mu 0 here. And so this is the second question. What if mu is not a constant but depends on rho? Even if rho is strictly positive. Okay? So for this, there are results. Okay, if what to say, the jump, okay, like the difference of viscosities. So mu1 minus mu2. If this is small. So if the viscosity inside and outside is very small, then things work out, but open in general. And this is open in general, but I'm talking always about inhomogeneous Navier-Stokes. So looking at the equation in weak form and looking at rho and mu as functions defining all the space. So another approach, which is not exactly the same and it's more traditional, it was done before, is what if we have a fluid, this is an interface, and we write Navier-Stokes, boundary conditions, and see what happens. So in that case, there are results for general viscosity jump, but assuming that the initial velocity is small, even in 2D. And the reason why, because they take this domain and they want to kind of linearize somehow, so they want to freeze the interface by like using something like the Lagrangian coordinates. But for that, they need the small velocity. Otherwise, this might change too much. So no matter the approach, like general initial data, so general density jump, viscosity jump, and initial velocity, that's open into it. Okay. I can mention a bit more about the viscosity jump, the small viscosity jump. So I will not write the theorem. The theorem is very similar to the previous one, that same conditions. In the end, you have propagation of travelers. So yes, I will only show some of the difference. So I will try to repeat. Well, it's a race, but the step that I wrote here for the H1 balance, and see where things start to fail. Okay, so as I said, I will do L2 balance, H1 balance, and later one should start doing time weight estimates and all those things. But right now, just the typical L2 and H1. So the L2 estimate doesn't really matter that we have viscosity jump. It's very similar. This is the diffusion that we obtain. So let's check the H1 balance. Better result. So now, before I multiply the equations by ut, and derivatives of u. If I do that, it's not going to work. And we will see now in a moment why it doesn't, or no, yeah, it doesn't work. So I'm going to multiply by the whole convective derivatives. So I'm going to denote this dtu, and I multiply by this one. I integrate by parts and use index notation. Okay. Now move this derivative inside. We have here a commutator for this part. So we obtain two terms. And here, yeah, like the commutator with the second part, which gives So two things I want to point out. Well, this term vanishes because the Kronecker curve with this we obtain divergence. So this goes zero, but this term doesn't vanish. So here we have to deal with the pressure. And the other thing, the reason I multiply by dTu is that now here, okay, here there is some computation to do, but if you just keep the first term, later you have to symmetrize. But if you keep this, you see that we have here minus dt partial. Okay, I put the result, okay, this is mu. Well, and because mu was a function of the density, and the density is transported, is just a transport equation. Here, what I just want to say is that okay, this ddt mu is equal to C. So I can put mu outside. And then from this balance, I'm obtaining that square rho dtu square plus, and I obtain some diffusion, which is 1/2 ddt. But what I put at the beginning. Yeah. And for the pressure, so two things. The first part, I think is more or less clear. We have to deal with the pressure. We only have the equation, so we need to write P in terms of the rest. So we are going to do the same as we did to obtain the linear projection. Take divergence of the equation, we obtain the Laplacian, and invert. So from that, there is no surprise. So one obtains that P is inverse Laplacian of all the other things, no? Of divergence of U plus divergence of, and this flag is here, and we obtain these three terms. Okay, I put the time weight, but we don't care about this right now. And E3 is similar to E1. Well, this is the last comment, okay, and I finish. I stop. So what did we do when there was no viscosity jump in this situation? We use a lot, many times, Lenskine inequality or Gallardo linear median partial. So L2, L4, L4. And when we have the L4 of gradient of U, well, in fact, I will do the same now. No? So, for example, E1 is less or equal than some constant. And now we have L2 L4 squared, And by the Ladislawski inequality, this is L2 two derivatives L2. So this is the problem now that before we had from the Stokes equation. So thinking of the equation in this form, so again, this is before that. It was immediate to obtain bounds in L2 for second derivatives in terms of dtu, so that to absorb it with the left-hand side. So now we don't have this. We have divergence mu, du, and we want, and this is the bad thing there, no? In general, I could say the equation like, okay, how do we control LP norms of the gradient of U for P bigger? And here it's where we need to use the smallness of the viscosity jacket. So it's kind of cheating because we are basically saying that if this is small, then I can add and subtract and write this like some constant mu bar, Laplacian of U, plus so from here I invert the Laplacian and I get that gradient of U is equal to 1 over mu gradient Laplacian minus 1 divergence and if I want, I can put an array projection because this is, so I will put here the array projection and the array projection. Now, this coefficient is small. These are singular integrals of 0 order. Take LP. So LP norm of the gradient is less or equal than this constant here. So some constant. These again are singular integrals. So no, I want to keep it. Sorry. So this is P divergence mu in LP. But I haven't gained much. This is still bad, no? We have the mu inside. But okay, let's just move this P and write it. So this is basically my equation. If I take the array projector here, is that good? Not completely. If you do that directly, if we substitute the equation, then we have one integral applied to rho, which is a patch. And then you can do that. Like rho is not in the space of multiplier in h minus 1. So you cannot do this directly. Instead, since we are doing the LP norm, do Gallardo here. So gradient of U in LP is whatever we have there, which is L2 to the power 2p times gradient of whatever we have L2 the corresponding power, and now we use the equation, and this is perfect because these are 0 order singular integrals, these are again singular integrals. So we obtain what we wanted, what we had in the homogeneous case, that any LP norm of the gradient is controlled by the gradient itself. Okay, I can just put here L2 T. Rho, I can just remove it. L2 1 minus 2. And in particular, we use it a lot for p equal to 4. And okay, I think, yeah, more or less I can stop there, just like one comment. In the end, we want to do the infinity norm of gradient U. And this works up to p less than infinity, because I was killing a lot of singular integrals. Sorry? Yes, but I want, I really need gradient U in L1 time L infinity. In fact, I need more than L infinity to propagate C gamma, but at the very least, I need this for uniqueness. And if I do that directly, I will obtain some BMOs, and then that is not possible. So before for the C1 gamma, this didn't appear. We were one derivative better than now. But this, you can see from the equation, like now. So this is now, and it was before. So before, two derivatives of U was like a jump function. But now, here we already have a jump. So we lose one more derivative. But before, if we wanted, for C1 gamma, there was no problem. But if we wanted to propagate the curvature to derivatives, we can write this as this. And then we obtain singular integrals applied to a patch. So this is not trivial. But if the patch is C1 gamma, then it is known that for even singular integrals, there is hope that this is bounded in L infinity. The easy compared to the new part is that here this function is independent of this one. So we can study first the regularity for dTu, and if this is smooth enough, this is a patch, and we can deal with all this as a patch. If we do this here, well, we cannot do that here because just so it's written here, no? If we try to do the L infinity, again we have similar integrals of a patch, but now it's applied to the same function that we had here. And well, this gets more complicated, and one has to get inside this operator. And with that, I finish, and thank you very much for coming, and on behalf of the other speakers.